Hello and welcome everyone. I'm your host Stefan Burns, geologist, geophysicist, space weather guy, here to update you on what's happening in Hawaii. This is the 48th eruptive episode of Kilauea Volcano, which makes this a record-breaking eruption because these lava fountains, while they do occur in Hawaii, Kilauea, it's not like it's every single day. Hawaii is one of the world's most active volcanoes, if not the most active. It's been very active for not only years, but decades, even centuries. But there is a period right now of heightened volcanic activity at the Big Island of Hawaii going back long time frames. So we're talking hundreds of years. So this is an exceptionally active period based off of our historic records and observational records, which have different time frames. You know, historic observations by the natives go back hundreds of years. More recent observations go back to like the 1800s or so. So the reason why this is a record-breaking eruption is because from 1983 to 2018, we were in what was known as the Pu'u'o'o eruption. So it's a 35-year-long eruption, which saw a dramatic increase in activity from Kilauea, and there were 47 lava fountain episodes that occurred as a result of the Pu'u'o'o eruptive cycle. And well, that was from 1983 to 1986 specifically. You notice that started off the whole 35-year cycle. Kilauea is now at 48 episodes, and in nearly half the time. This is from 83 to 86. We see the height of these lava fountain episodes started off small. This is Pu'u'o'o. Really increased up, got very, very tall. Here is what's happening right now. So this is showing 45, 46, 47. Now we've had episode 48. We're in it. So we've broken the record for Pu'u'o'o, the beginning of that 35-year eruptive cycle, which was the most active Kilauea has been in hundreds of years, according to geologists and record keepers and more. So that is notable. It's happened also in about half the time. These eruptive episodes started up in late 2024, specifically December 2024. And so it's been about a year and a half now, because it's June 1st today, 2026. And so almost exactly a year and a half, a little bit less actually. This is about 3 years in length. So in nearly half the time, there have been the same amount of lava fountain episodes plus one. So, you know, this eruptive cycle here, the Halema'uma'u eruptive cycle, perhaps this is all it is. You know, there's some more lava fountain episodes, maybe there's dozens more, but that's it. And this kind of dies out after a few years. This could be the beginning of a decadal long active cycle for Kilauea. We simply don't know. But there's quite a bit of evidence that this is the start of something bigger. And so we'll get into that. Here we have our monitoring data for Kilauea, and this is just showing you the most recent information. We measure the tilt and the inflation, the deflation of this caldera. So we see here for the past 2 days, when the tilt goes down like this, that's indicating that the eruption has started. That's obviously the case. As we see here, it's going. They're about 500 feet tall. We see for our past week that we've really dropped down. If we go to our past month, you see the prior eruptions, 47, 46. Here you can see we're about, well, we're a little bit more than halfway, I would think. We're probably about 3/5, because these lava fountain episodes have been lasting like 8 hours, 9 hours. Recently, these ones right here, look at that data too. Let me get that in view for you. So we're about 3/5 away through this eruption. It'll go on for about probably another 4 hours before it ends up. So before the sun goes down, I think this eruption will be done. Unless there's some dramatic change in how it pumps this magma out to the surface. If we see here, our past 3 months, you see that we've been having these kind of short, small eruptions. Look at this one. That was quite a bit larger, right? Its tilt was much higher and it dropped significantly. So it was about the same length of time, maybe a little bit longer. You know, they can be like 10, 11, 12 hours, But when you have a lava fountain going up 1,200 feet versus 500, right, the volume, the overall discharge is much higher per second than it is for these. You've noticed that we've been on this uptrend with inflation. And we had a big magnitude 6 earthquake strike the west side of the island about 10, 11 days ago. And that clearly altered this eruptive cycle, because if you go here, we see exactly when that earthquake occurred. Interesting to note is that you see these changes in the tilt, and therefore the inflation, deflation, before and after that magnitude 6, which was in the oceanic crust like the lithosphere, and it wasn't directly related to the volcano. It was more from the weight of the Hawaiian Islands on the thin oceanic crust, causing there to be, an earthquake and a fracture event. But we see how it's all connected together, because look at how we did get this preliminary signal. Now, at the time, that wasn't necessarily abnormal, because we see other things like that in this record. We see dips right here. We see a little dip right there. We're going to look at the long time frame in just a second. But it is perfectly positioned right in the middle of this kind of wave motion right there. So this eruptive cycle definitely has not been as smooth or as short as the others. Look at the others basically just recharge really quickly, drop back down. Here, for example, right, they're pretty short, maybe 10 days in between. This one has been quite a while coming, and it did not happen on the 31st of May. It happened today in June. So the last one was on the 13th. No, I think it was maybe the 15th of May, 16th of May, somewhere around there. So if we go to our long-term data right here, check this out. I'll turn myself off really quick. And you'll notice these eruptive episodes, they started December 2024. They were quite brief and rapid at the beginning. Then they started to get bigger and bigger. So this is when we had some really big episodes. You notice in here for the episodes in like the late 30s and early 40s, really big discharge events. Huge lava fountains going up 1,600 feet, 1,700 feet. This is 500, 600, maybe, well, yeah, about 500 meters or so. Maybe 550, 600 meters, yeah. So, but then look how it recently started to coil up again. And so the overall magma chamber was declining with these big ones, really discharging, but then inflating all the way back up, though a little bit less each time. Now there has been this positive inflation trend where Kilauea will discharge, but not as much. And this one actually really pushed us over the prior, you could say, trend line for the other eruptions. And interesting that earthquake occurred. So the whole system, geologic system of Hawaii, is super interconnected and more complex than we realize, and more intelligent, I would say, personally, than I think most modern or mainstream scientists would care to say. But I also am someone that believes that everything is conscious, and consciousness is inherent in the quantum field and things of this nature. And while most geologists aren't learning about quantum mechanics and such, so that's kind of a different conversation. But it is interesting to see how this non-related earthquake did start to change the parameters, and we're almost at this decision point of, okay, are we going to continue to inflate or are we going to continue to deflate? So this is kind of a critical juncture moment. And also, again, it's at this time where we just passed the number of lava fountain episodes from the Pu'u'o'o eruptive cycle back in 83 to 86. So that's quite interesting. The difference now versus then is that we have a whole new complex of magma storage on the Big Island. And of course, this is always changing. It's been around for millions of years, so I'm sure things like this have formed, gone away, formed again. Maybe this is a reactivation of an old structure from 2,000 years ago. It's kind of hard to say. But we've been having this earthquake swarm here near Pahala since 2018. After the Pu'u'o'o eruptive cycle ended, we started getting a bunch of microseismicity here, tens of thousands of earthquakes going from 30 kilometers to about 50 kilometers in depth, forming these horizontal sills of magma storage. So SILLS, a sill. You have dikes where it's like a vertical or a slanted intrusion of magma, and then you have sills which are horizontal. And think of it like a giant magma lake, and then you have rock layers on either side. Everything, of course, is highly pressurized, but it is magma. There's also zones that are like melt zones, they call them, crystallized mush zones, where there are some crystals and cooling, but you also still get some magma in there as well, and it's all kind of floating around together. It's like semi-solid, semi-liquid, and they can, if you get a big push of magma from depth, those can suddenly activate and cause a big discharge. So all these earthquakes here under Pahala, not only is there a new large magma reservoir that exists there, it also connects Mauna Loa and Kilauea together. This is a nodal point for this larger Hawaiian hotspot system. There's other magma chambers, other sills and dikes that exist. They're all over the place. I mean, for example, Kilauea is not just confined to this crater. It also extends all the way out to the eastern side of the island. This is what brought the Pu'u'o'o eruptive cycle to an end in 2018, the Leilani Estates rift eruption. Lasted a few months. A day after it began, there was a magnitude 6.9 earthquake that struck south of Kilauea along the flank, right in this zone here. There's been, everything is connected together in unique, exciting ways. You still have active volcanism. There's one volcano in Hawaii that's still active. There's even old volcanism on Oahu. Some people are concerned about there. I wouldn't be so concerned about Oahu in terms of volcanism because that's pretty far away from the hotspot now, but you never know. It really depends on just how much energy is coming up from the depth. And if it can create these fracture networks to expand and then transfer this magma further and further, and there's continuous new injections, maybe you could see activation of volcanism on Oahu. But this is a pretty far-flung scenario, but it's certainly geologically not impossible. It just would have to happen. But Maui certainly can happen. Volcanoes, there's a volcano here on the north part of the island, hasn't been active for a long time, but it could become active, right? We also have this seamount over here, where we get active. This is one of the new volcanoes for the Hawaiian Islands. That could be the focus of activity. Mauna Kea hasn't had an eruption in quite some time. We're talking thousands of years, but it still has a magma chamber. It's partially crystallized, partially active still, and with a fresh injection of energy, it could certainly reactivate. And Mauna Loa will definitely be active again in the future. I mean, I think it's something like 80% of the slopes of Mauna Loa are fresh lava flows over the past 5,000 years. It's a large amount. So Kilauea is going. Now we can look at this. This is interesting. We see that the magnesium oxide concentration has changed since episode 1 to episode 42, which I think this data just goes up to episode 42, but maybe these are, or I think, yeah, these are different samples of each episode. So we see that our magnesium oxide weight percent was here around 7 for episode 1, and just a little higher for episode 2. Quickly shot up to about 7.6, dipped down. Now it's maintaining these high levels and even setting some really high amounts right there, as you can see. Now this is important because magnesium oxide is a component of magma and just in general the composition of the mantle. So you get less magnesium as it becomes more felsic. You have mafic rocks, you have felsic rocks. Mafic rocks are typically black, they're basaltic, they're less refined material from the mantle. So it's like as the earth actually is at depth, that mineral assemblage, that's a mafic rock. Felsic rocks are more differentiated. You have different chemicals and different minerals. So it'll be a lot of quartz, a lot of like feldspar. and it'll be, the actual color of the rock will often be white or gray or pinkish or maybe even red, like with a really strong potassium feldspar, especially like a potassium feldspar rhyolite. It'll be like a really bright red almost. And the compositions vary depending on the setting, the context, and more. Well, Hawaii, if we go back to our wonderful volcanic eruption here, Hawaii is an ultramafic shield volcano. So you're getting magma straight from the mantle coming up with very little alteration. The amount of gas dissolved within this, this is lava here at the surface. Magma is below the surface, lava is at the surface. But the amount of volatiles in the magma for Hawaii, in the Hawaiian hotspot, is very, very low. Still has some, we'll talk about it, but it's not that high. Usually you get more volatiles, this would be gas and other compounds, right? In these highly silicic magmas, there's not that much silica in this compared to a felsic one. For example, like Mount Rainier, or Cascadia, or Mount Etna, or something like that. There'll be a lot more felsic, silicic, and sticky. So kind of the pressure builds up, and then those gases are there, pressure, 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 and boom, you get a huge explosion. Here at Hawaii, I mean, this is incredible, 500-foot lava fountains, but you're not getting a giant explosion that can, literally cause a volcanic winter. And what we're seeing with these eruptions is that our magma is obviously being sourced from even more primitive and deeper parts of the mantle than it was initially. You did get this burst right there, this push, but we see that now because our magnesium oxide concentration is going up, we can fairly reasonably assume that these are more primitive, undifferentiated magmas from deeper in the mantle. And that is what the Hawaiian hotspot mantle plume is. It is this natural convective flow of energy coming up from the deep earth. There's a variety of ideas as to how that's created, why that exists. But what this shows us is if there is a higher volume push of magma, then things could escalate in Hawaii, like a rift eruption that takes out 400 homes or things of that nature. It's certainly possible. It's happened many times. It will happen again in the future. So you need that sort of connection to the deep mantle for that to be possible. That's the thing. And the fact that now we're seeing very clear signs of that with the mineral composition, the fact that these lava fountains are happening so frequently. Now it's a record amount of 48, right? All these, in general, giving an indication that it's more likely that activity will continue to increase in Hawaii rather than decrease. Now, that's not guaranteed, but that's probably the case. We're probably more likely to be in a new long volcanic cycle with Kilauea, and maybe Mauna Loa activates at some point too, rather than, okay, we have two years of fountains and then everything goes quiet for 40 years. I don't think that's as likely, especially when you consider the fact that there is this connection between volcanic activity and solar activity, and when solar activity is declining, there is a small but statistically significant correlation showing that volcanic activity increases. So they're anti-correlated. Solar activity goes down, volcanic activity goes up. And while we're going into the descending phase and the minimum phase of solar cycle 25, solar minimum isn't until like 2030 or so, but we're inexorably marching that direction. You don't have solar maximum last for 100 years straight. It's 3 years, basically, you're done. So we are moving that direction. Now, before we get into reading a little bit and learning more about volcanoes and Hawaii and the geology and more, let's just quickly look through this, this informative webpage describing the difference between lava and magma. And this is from National Park Service. And so we'll read through this. Lava, according to native Hawaiian traditions, molten lava is the manifestation of Pele, the volcanic deity and creator of new lands. She is a rejuvenating and creative force, reshaping the landscape with each eruption. Indeed, molten lava that reaches the surface during volcanic eruptions is still adding mass to the island of Hawaii. So one of the few places in the world that's actively growing right now. The island itself is made up of flows that have been built upon one after another over many thousands of years, even millions of years. Here we see a great example of that, some giant lava flow. Two types of lava can be seen in Volcanoes National Park. And so this is Pahoho and A'a. I'm not sure I'm saying that last one correct. But Pahoho lava appears smooth and ropey. It moves slower and stays hotter than A'a lava. And when flowing, it can form lava tubes and may have many flow units known as toes because it's more runny and less viscous. A'a lava, by contrast, appears rough, jagged, and chunky. It moves fast with high velocity and loses heat quickly while flowing. A'a lava is much more viscous than Pahoho and flows in fewer, larger channels. Most flows consist of both types of lava, though the proportion of each can vary widely. Pahoho upstream often changes to A'a lava downstream, although it's possible the reverse of that is also seen, though it's just less frequent, less often observed. Lava or magma. Magma and lava are the same substance, but in different places. It's really simple. Magma refers to molten rock still within the earth, whereas lava is magma that's now breached to the surface. So if it's at the surface, we're seeing lava. These are lava fountains that we're seeing here in Hawaii, though you'd be forgiven if you say they're magma fountains. I mean, at the end of the day, if you're not a geologist, yeah, it's good to know the nomenclature, but I think we'll all understand what you're saying. But these are lava fountains because it's at the surface. It's magma below the surface. Similar to how a meteor is a space rock in space, it becomes a meteorite when it enters into the atmosphere. How hot is lava? The temperature of erupting lava from Kilauea is about 2100 degrees Fahrenheit or 1150 degrees Celsius. Erupting lava cools quickly when it is exposed to air, hundreds of degrees per second, though rocks may steam for years after an eruption. That's interesting. Must be like residual heat trapped. Of course, it's going to cool off even quicker if it's exposed directly to the ocean. And here is probably the most informative part of this article. So I'm showing you this. Why don't Hawaiian volcanoes explode as violently as others? Although powerful, Hawaiian volcanic eruptions are famous for being relatively benign and approachable in comparison with volcanoes elsewhere. Hawaiian eruptions are not nearly as explosive as those like Mount St. Helens in 1980. The reason for this lies in the chemical composition of the magma that feeds these volcanoes. Hawaiian magma contains comparatively little silica and is highly fluid. Accordingly, it can flow relatively freely and release these gases and volatiles that I mentioned earlier very easily. On the other hand, the magma of volcanoes located along the edges of tectonic plates, such as Mount St. Helens, has a different composition that makes it much more viscous, i.e. less fluid. It tends to hold more gas and break apart, possibly explosively during eruptions. The easy flowing, fluid nature of lava from Hawaiian volcanoes contributes to their space and is why they are referred to as shield volcanoes. Lava easily flows down the sides of the volcano, giving it a rounded appearance like a Roman warrior's shield. So here we see the composition breakdown for Mount St. Helens versus Hawaii, two different types, basalt versus dacite. You see that the silicon percentage for Hawaii is about 50%. For Mount St. Helens, it's getting closer to 65%. You see also that there's much more aluminum in the Mount St. Helens lava, where there's less aluminum and a lot more iron. And here we see that magnesium. Look at how much magnesium is in the Hawaiian basalt versus the Mount St. Helens dacite. Quite a bit more. Calcium is also a lot higher. You get a lot more of these other compounds besides just silica. So that's one reason why it flows very easily. And you'll also notice, interestingly, with Hawaii, a huge amount of titanium comes out, because there are these magnetic compounds like titanomagnetite that deliver titanium to the surface. So we really are sampling the deep magma of the mantle with Hawaii. And when we see that even within Hawaiian basalt, that magnesium oxide percentage is going up, that we're tapping different sources from different depths in the mantle and showing that there's new connections being formed or old ones reactivating. But this is a sign that there are active changes unfolding. This is not just your ordinary eruption at Kilauea. Eventually, I think we're going to see what really does manifest from all of this. So yeah, there's quite a lot happening. And let's just learn a little bit more about all of this. I have my book here on geology, and we'll just read through a little bit. Yeah, I think this is a good place to start. Why do volcanoes erupt? Once formed, melt, which is less dense than surrounding rock, will buoyantly rise towards the surface. So in the Earth, you have a lot of rock that's under extreme temperature, so you think it'd be molten, but it's also under extreme pressure. That pressure changes the phase diagram, as we call it, of whether it's phasing of whether it's a solid, liquid, or gas. And well, for gas, you're not going to get it. But if you have high temperature but also high pressure, it'll likely stay solid. If the pressure goes down, you can now take these rocks that exist at depth and melt them. That's what's happening with this hotspot. For some reason, there is this low pressure column that exists. The hotspot itself is low pressure. Now, if you ask me, there is this idea that the Earth, perhaps the deep Earth, has georeactors, so natural nuclear fission reactions that occur. And when you have nuclear fission, you generate light elements like helium. There's a whole bunch of light elements that you would create. Well, light elements, of course, are gas, and they don't easily become liquid or solid. Helium specifically, has to basically be like super chilled down to become a liquid. And so that would reduce the pressure. And they're going to want to escape up because the gravity is so much and they're very light. They're going to want to move away from gravity and go into the atmosphere and even out into space. So if you do have this active generation of helium through georeactors, and the hotspots connected directly to them, you would get that to flow out. And what do we see in Hawaii? We see greatly elevated counts of Fe3 versus Fe4, which is indicative of georeactors and nuclear fission. Now, the conventional explanation is that there are these reservoirs of helium from the accretion of the planet, and that they're as old as like 4 billion years. But how you have these helium reservoirs and why that helium just hasn't gone up makes really no sense if you think about it. Because again, helium, you do to get this natural density differentiation that occurs chemically. There's chemical differentiation, there's density and gravity-driven differentiation. So why you'd have this huge helium reservoir that's not going anywhere, it doesn't really make sense. It makes more sense that's actively being generated. But do your own research, make up your own mind. It makes sense though. We see this observationally in Hawaii, we see the low pressure, we see the active generation in magma. So it's all a very coherent theory. Because the density of crustal rocks decreases towards the surface, ascending magma may reach a level where the rocks above are less dense. Should this occur, the molten material begins to collect, forming a magma chamber where it may reside for an extended period before it either A, solidifies, or B, some of it ascends further. Only a fraction of magma generated at depth ever reaches the surface. Now, one thing to keep in mind, we're talking about Hawaii versus Mount St. Helens. Mount St. Helens is one of these volcanoes generated from the subduction off the coast. And then as that plate subducts underneath the North American plate, it's loaded with water, and you get this water to basically like precipitate out effectively. You form these fluid channels, and not only does the presence of water cause there to be new mineral reactions to occur, it also lowers the pressure, generating melt, which contributes to this whole process. But water itself also tends to increase the fluidity of magma because it reduces polymerization, which is these long silicate chains, by breaking silicon-oxygen bonds. So water is very important to keep in mind here, and you'll find it interesting to know that there are these vast freshwater reservoirs that exist at Hawaii that extend not just to the island and the edge, but actually off the island. So you have the ocean all around, but there's these deep oceanic plate freshwater reservoirs that have been identified that are huge, especially around the Big Island. So you see how this is all kind of connected together. Clearly there's water here, right? You have some flow of energy from the deepest parts of the Earth due to the mantle, due to low pressure. Why is that? Why does that exist? Well, there's this super anomalous He3 to He4 ratio that we observe with Hawaiian lavas. And we see that they're able to put on these massive lava fountains, but people right now at the park are watching this from the overviews, you know, a mile and a half away. There's really nothing to, as of right now with this eruption, I would not hesitate to go and watch it. You know, I did that back in August of 25. It was great. There have been some that have been quite crazy, and they told people to excavate because there's ash and tephra and everything raining down, but that's not really this one in that sense. Though there is pele hair and ash and some stuff coming down in certain areas, as we discussed earlier on when I gave you that update. Triggering a volcanic eruption. One of the simplest mechanisms for triggering a volcanic eruption is the arrival of a new batch of melt into a near-surface magma reservoir. Now I'm going to stop there just for a moment, because what did we just talk about? We looked at the earthquake activity here, and we can actually switch this to be the past month, so you really can see this Pahala Sill complex. See all these earthquakes that have occurred around Pahala, right? That's showing this new magma reservoir that exists from about 30 to 50 kilometers down that connects Kilauea and Mauna Loa, okay? And of course, also, we mentioned this, how we're seeing changes to the composition of the magma as measured by magnesium oxide, indicating it's even more mafic. It's like ultra mafic now, which means it's even more so from the mantle, undifferentiated. So going back, I'll repeat what I just read. One of the simplest mechanisms for triggering a volcanic eruption is the arrival of a new batch of melt into a near-surface magma reservoir. It's probably what's happening right now and will continue to unfold. This phenomenon can often be detected because the summit of the volcano begins to inflate months or even years before an eruption begins. The injection of a fresh supply of melt causes the pressure in the magma chamber to rise until cracks develop in the rock above. This in turn mobilizes the magma, which quickly moves upward along the fractured rock, often generating quiet outpourings of lava for weeks, months, or even years. Here, it's now been 1.5 years. This mechanism is thought to have triggered numerous large eruptions of basaltic lava along the East Rift Zone of Kilauea. And this isn't talking about, you know, Hawaii specifically. This book's just a general textbook on geology, but there it is, talking right about the East Rift Zone of Kilauea, because we know so much about these volcanoes on the Big Island of Hawaii and with Maui. This mechanism is thought to have triggered, the most recent eruptive phase in this region has been almost continuous since it began in 1983, this book being written before 2018. This is the Pu'u'o'o eruptions. Although the influx of a fresh supply of magma is thought to trigger many eruptions, it does not explain why some volcanic eruptions are explosive. The role of volatiles in explosive eruptions. All magmas contain a small percentage of water and other volatiles that are held in solution by the immense pressure of the overlying rock. As a magma body evolves, the earlier formed iron-rich minerals tend to sink, leaving the upper part of the reservoir enriched in volatiles and silica-rich melts. So there's this natural differentiation that occurs, density-driven and gravity-driven differentiation, crystallization differentiation, which is related to that, and then also chemical differentiation. They're all connected together. There's always these active processes that are taking what's fairly homogeneous, which is this deep magma melt source from the mantle, and differentiating it. But what's unique about Hawaii is that there's very little differentiation in general that occurs, but it still does occur. Should this volatile rich magma rise or the rocks confining the magma fail, a reduction in pressure ensues and the dissolved gases begin to expand and form bubbles. This is analogous to opening a warm soda and allowing the carbon dioxide bubbles to escape. At temperatures of 1000 degrees Celsius and low near surface pressures, these gases can quickly expand to occupy hundreds of times their original volume. Very fluid basaltic magmas allow the expanding gases to migrate upward and escape from the vent with relative ease. As they escape, the gases may propel incandescent lava hundreds of meters into the air, producing lava fountains. Aha, there we go. As although spectacular, such fountains are mostly harmless and not generally associated with major explosive events that cause great loss of life and property. Rather, eruptions of fluid basaltic lavas, such as those that occur in Hawaii, are generally quiescent. On the other hand, highly viscous, silica-rich magmas may produce explosive clouds of hot ash and gases that evolve into buoyant plumes called eruptive columns that extend thousands of meters into the atmosphere, perhaps even into the stratosphere. When viscous magma ascends, the developing gas bubbles do not easily escape, but rather cause the molten material to expand, resulting in a gradual increase in the internal pressure. And should the pressure exceed the strength of the overlying rock, fracturing occurs. The resulting breaks lead to a further drop in the confining pressure, which in turn causes even more gas bubbles to form, and this chain reaction often generates an explosive eruption, in which magma is literally blown into very fine fragments, ash, that are carried to great heights by rising hot gases. So it's often a gas component more so than a magma or lava component. I mean, the lava is important, obviously. Like the magma and lava is obviously important, but because of how the volume can change so quickly, going from dissolved gases in solution effectively to now gas actually out of solution 100, 200, 500 times more voluminous, then that's your boomshakalaka. Mount St. Helens is a great example of this. The 1980 eruption basically marked there being a drop in the confining pressure, which then triggered the collapse. You had the flank of the volcano collapse, which then caused there to be a drop in the confining pressure, and then you got the big explosion at Mount St. Helens. As magma in the uppermost part of the magma chamber is forcefully ejected by the escaping gases, pressure on the molten rock directly below drops. Thus, rather than a single bang, volcanic eruptions are really a series of explosions. This process may logically continue until the magma chamber is emptied, much like a geyser empties itself of water. However, this generally does not happen. Only within the upper portion of the magma body is the gas content sufficient to trigger a steam and ash explosion. Most eruptions are followed by quiet emission of degassed lavas. For example, during the 6 years following the 1980 Mount St. Helens eruption, episodic extrusions of lava built a large dome on the crater floor. A second dome building event began in October of 2004. Although these eruptive phases produced some ash plumes, they were benign compared to the May 18, 1980 explosion. To summarize, the viscosity of magma plus the quantity of dissolved gases and the ease with which they can escape determines to a large extent the nature of a volcanic eruption. And in general, hot basaltic magmas contain a smaller gaseous component and permit those gases to escape with relative ease as compared to more highly evolved silica-rich magmas. This explains the contrast between gentle outflows of fluid basaltic lavas in Hawaii, and they put gentle in quotes. This is still, you would not want to be standing right there, okay? You know, you just would not want to be there. It would be over very quickly for you. But comparing this to, you know, explosive eruption like Hunga in 2022, VEI 5.8, just that's quite a bit different. So there's this contrast between gentle outflows of fluid basaltic lavas like in Hawaii with the explosive and sometimes catastrophic eruptions of viscous lavas such as from Mount St. Helens, 1980, Mount Pinatubo in the Philippines, 1991, Sufri Hills on the island of Montserrat, 1995, Hunga Tonga, 2022, etc. The gaseous portion of most magmas make, well, here, we'll learn a little bit more about gases. Magmas contain varying amounts of dissolved gases held in the molten rock by confining pressure, as we discussed, just as carbon dioxide is held in soft drinks. So think of your Coca-Cola fizzing, right? Very similar. As with soft drinks, as soon as the pressure is reduced, the gases begin to escape. Obtaining gas samples from an erupting volcano is difficult and dangerous, so geologists usually estimate the amount of gas originally contained within the magma. The gaseous portion of most magmas makes up 1 to 6% of the total weight, with most of this in the form of water vapor. Although the percentage may be small, the actual quantity of emitted gas can exceed thousands of tons per day. The composition of volcanic gases is important because they contribute significantly to the gas that make up our planet's atmosphere. Analysis of samples taken during Hawaiian eruptions indicate that the gases are about 70% water vapor, 15% carbon dioxide, 5% nitrogen, 5% sulfur dioxide, and lesser amounts of chlorine, hydrogen, and argon. Sulfur compounds are easily recognized by their pungent odor. Volcanoes are a natural source of air pollution, including sulfur dioxide, which readily combines with water to form sulfuric acid. In addition to propelling magma from a volcano, gases play an important role in creating the narrow conduit that connects the magma chamber to the surface. First, high temperatures and the buoyant force from the magma body crack the rock above, then hot blasts of high-pressure gases expand the cracks and develop a passageway to the surface. Once the passageway is completed, the hot gases armed with rock fragments explode its walls, producing a larger conduit. Because these erosive forces are concentrated on any protrusion along the pathway, the volcanic pipes that are produced have a circular shape. As the conduit enlarges, magma moves upwards to produce surface activity. Following an eruptive phase, the volcanic pipe often becomes choked with a mixture of congealed magma and debris that was not thrown clear of the event, and before the next eruption, a new surge of explosive gases may again clear that conduit. Occasionally, eruptions emit colossal amounts of volcanic gases that rise high into the atmosphere, where they may reside for several years. That's exactly what happened with Hunga Tonga. There was a huge amount of water vapor injected into the stratosphere, which is still there. About 50% of that water from 2022 is still stored in the stratosphere. The stratosphere typically doesn't have that much water. So it was a very significant geologic event, geophysical event, that's still affecting our climate to this day. Some of these eruptions may have an impact on Earth's climate, and well, yeah, they do. Here's a section directly on Kilauea. Let's read this. Well, let's read a little bit about shield volcanoes too. It's the section before. Shield volcanoes are produced by the accumulation of fluid basaltic lavas and exhibit the shape of a broad, slightly domed structure that resembles a warrior's shield. And I should be able to pull up a picture of a shield volcano for you, because I know that'll be helpful to see it. Though I think most of you probably know what a shield volcano looks like. So here we go. So this is a shield volcano, and behind me you'll see the stratovolcano. So you see that the slopes of the stratovolcano are much higher, it builds up, and that adds that confining pressure. These are the ones that explode very explosively, or they erupt very explosively. Shield volcanoes, much shallower slopes. They really extend out because these lavas really go ahead and flow out from the base. And you'll see this magma chamber. This is a visualization, of course, but here we see this conduit going up. Here we see this dike, and what Hawaii has is actually a whole bunch of vertical sills. So imagine this magma actually in these horizontal sheets going like this. And what's been happening with Pahala is these earthquakes, magma keeps pushing in, creating new fractures, which then get filled in, and then it's creating new fractures, and it's expanding this whole network. So there's a lot of magma now stored at depth, which was not there at the end of the Pu'u'o'o eruptive cycle. And again, that was the biggest in like hundreds of years, going from 83 to 2018. Now we have an even more developed magma reservoir system under Pahala, and we've seen these lava fountain episodes reach number 48. Pu'u'o'o only reached 47, and in half the time. So I personally think we're in a volcanic supercycle with Hawaii. That doesn't mean that the island's going to explode, but we're probably talking about more fissure eruptions, more lava flows, more destruction, unfortunately. Like, this is all real, and it's happening. It's real, and it's happening. Okay. Most shield volcanoes have grown up from the deep ocean floor to form islands or seamounts. For example, the islands of the Hawaiian chain, Iceland, and the Galapagos are either a single shield volcano or the coalescence of several shield volcanoes. Some shield volcanoes, however, occur on continents. Included in this group are the rather massive structures located in East Africa, like Suswa in Kenya. And that's because there's the East African Rift Valley, which is splitting Africa apart from the African superplume, which is made up of very mafic magma, and it's therefore able to make shield volcanoes even though it's going through the continent itself. Extensive study of the Hawaiian Islands confirms that each shield was built from a myriad of basaltic lava flows averaging a few meters thick. Also, these islands consist of only about 1% pyroclastic ejecta, so very, very little. Mauna Loa is one of 5 overlapping shield volcanoes. Let's actually pull Google Earth up again so we can see this. And I actually wanted to show you something else on Google Earth too, related to all this. Very interesting. Kind of a geologic mystery. So let's pull it up. Go to Hawaii. Okay. Mauna Loa is one of 5 overlapping shield volcanoes that together comprise the big island of Hawaii. From its base on the floor of the Pacific Ocean, right, this is the oceanic plate, the Pacific plate, the oceanic crust. Mauna Loa is over 9 kilometers or 6 miles high, exceeding that of Mount Everest. So it's a very, very, very big mountain. But it's not as tall as Mount Everest over the surface of the ocean because most of it's actually under the water. This massive pile of basaltic rock has a volume of approximately 40,000 cubic kilometers that was extruded over a period of nearly 1 million years. For comparison, the volume of material composing Mauna Loa is roughly 200 times greater than the amount of material composing a large composite cone such as Mount Rainier. Yeah, let's check it out. Mount Rainier is a big volcano. Mauna Loa is 200 times bigger. Here's Mount Rainier. So we don't want Mount Rainier to explode, that's for sure. This would be a very, very destructive eruption. Kind of look at it from the side here. Right, so that's pretty cool. It's a big, big volcano. Thankfully, hasn't had a big eruption in some time. But we could go back to Hawaii, the wonderful magical island of Hawaii. Most shield volcanoes, however, are more modest in size. For example, the classic Icelandic shield Skjaldbreiður rises to a height of only 600 meters, 2,000 feet, and is 10 kilometers, 6 miles across its base. Despite its enormous size, Mauna Loa is not the largest known volcano in the solar system. That would be Olympus Mons, a huge shield volcano on Mars, 25 kilometers high and 600 kilometers wide. So that's pretty wild. Young shield volcanoes, particularly those located in Iceland, emit very fluid lava from a central summit vent and have sides with very gentle slopes that vary from 1 to 5 degrees. Mature shields, as exemplified by Mauna Loa, again, this is Mauna Loa right here, have steeper flanks about 10 degrees while the summits are comparatively flat. During the mature stage, lavas are discharged from the summit vents as well from rift zones that develop along the slopes. Most lava is discharged as the fluid pahoho type, but as these flows cool down slope, many change into a clinkery a'a flow. Again, that more sharp and angular, and you'll shred up your hiking boots on a'a like instantly, unless you're walking very carefully. So if you go to explore Hawaii, like the Big Island, and you want to walk around on the lava because there's places you can do that, make sure you bring like an extra pair of shoes, or you buy a pair of disposable shoes because they'll get shredded on some of them. It's quite crazy to see it in real time. Like 2 days later, shoes are gone. Once an eruption is well established, a large fraction of the lava, perhaps 80%, flows through a well-developed system of lava tubes, which I've explored on the Big Island. They're really crazy. If you go there, I recommend you do that too, or anywhere that there's lava tubes. I've explored them in Iceland as well. I think there's some lava tubes in California, probably. They're all over. 80% will flow through the lava tubes, and this greatly increases the distance lava can travel before it solidifies. Thus, lava emitted near the summit often reaches the sea, thereby adding to the width of the cone at the expense of its height. Another feature common to a mature active shield volcano is a large steep-walled caldera that occupies its summit. Mauna Loa's summit, and here it is. Mauna Loa's summit caldera measures 2.6 by 4.5 kilometers. And let's just see how close that is. There it is. That's about 2.8 kilometers right there. And look at how it drops. Oh, that's behind me. But here's the elevation drop. About a 100-meter drop across that. And actually, if we go back and go more like this to get our cross section, here we see that caldera going up, drops, flattens, goes up a little bit, drops again. Pretty cool. And yeah, it says here that the average depth for Mauna Loa's caldera is about 150 meters. Calderas on large shield volcanoes form when the roof above the magma chamber collapses. This can occur through the evacuation of a magma reservoir following a large eruption, or as magma migrates to the flank of the volcano to feed a fissure eruption. So that is important to know as it relates to Pahala. Now, all these sills that are being formed are at depth, 30, 50 kilometers down, right? But they are quite thick at 100, 200, 300 meters in thickness, and there's quite a lot of them. So if you were to have a rapid evacuation of melt from Pahala to, let's say, Mauna Loa or Kilauea, one of the two, both, we could see quite a bit of subsidence suddenly hit Pahala if they weren't to get recharged. You wonder how that, maybe some big earthquakes would then cause there to be that collapse event. I'm not talking like end of the world stuff here, but this is important to know. Especially if you live on the island, you should be very aware of the geology. At least I would be. In the final stage of growth, the activity on mature shields is more sporadic and pyroclastic ejections are more prevalent. Further, the lava increases in viscosity, resulting in thicker, shorter flows. We even see that very nicely here with our satellite imagery. And that's because just as simply as a shield volcano just builds up, there is just simply going to be more differentiation that occurs. So even though it is a very basaltic and a mafic lava, or even ultramafic with Hawaii, as it has to move up and up and up and up, and there's more time for it to cool, there's more time for crystallization, differentiation, all this stuff, you can start to develop the magma into a more explosive type. Or it has time to kind of cool off and then it gets reactivated. You get the idea. These eruptions tend to steepen the slope of the summit area, which often becomes capped with clusters of cinder cones. This explains why Mauna Kea, a very mature shield volcano that has not erupted in historic times, has a steeper summit than Mauna Loa, which erupted as recently, in this book, as 1984. Though I think it's had a more recent eruption. I think it was 2022 that there was a small eruption in Mauna Loa. Astronomers are so certain that Mauna Kea is, in general, over the hill, that they have built an elaborate observatory on its summit, housing some of the world's finest and most expensive telescopes. Well, I mean, maybe it's over the hill in our lifetime, but I think on the geologic time frame, I don't think Mauna Kea is done. But we'll see, you know. But all these telescopes up here, for sure, could be victims of some big eruption in the future. Probably hope not, because it's really cool stuff that they're doing. But look at all these cinder cones, right? So this is why it's amazing to, like, take a geology class or get a book like this, and then actively, while you're reading through it, you know, engage with what it's talking about, because then you can see it in real time. Look at all these cinder cones around Mauna Kea. It's really, really cool. Kilauea, Hawaii, eruption of a shield volcano. And we'll stop after this section with the reading, and then I'll sign off. Well, I'll take a couple questions, and then I'll sign off. We had a big super thanks come in, so I want to get to that. Kilauea, the most active and intensely studied shield volcano in the world, is located on the island of Hawaii in the shadow of Mauna Loa. More than 50 eruptions have been witnessed here since record keeping began in 1823. Now, today, we're in the 48th eruptive episode, but this is all considered one eruption. This is all the, this is effectively the Halema'uma'u eruptive cycle that began in 2024. So it's all considered one eruption. The Pu'u'o'o eruptions are all considered one eruption. Though, of course, this is 48 lava fountain episodes now. And we'll actually keep it here. Might as well show Kilauea when talking about it. Several months before each eruptive phase, Kilauea inflates as magma gradually migrates upward and accumulates in a central reservoir located a few kilometers below the summit. For up to 24 hours in advance of eruption, swarms of small earthquakes warn of the impending activity. Most of the activity on Kilauea during the last 50 years occurred along the flakes of the volcano in a region called the East Rift Zone. A rift eruption here in 1960 engulfed the coastal village of Kapoho, located nearly 30 kilometers, 20 miles from the source. The longest and largest rift eruption ever recorded on Kilauea began in 1983 and continues to this day. This book, again, being a little old now. This is from 2005, okay? So this is still well in the middle of the Pu'u'o'o eruption. That ended 2018 and continues to this day. The first discharge began along a 6-kilometer, 4-mile wide fissure where a 100-meter, 300-foot-high curtain of fire formed as red-hot lava was ejected skyward, so a fissure eruption. They have a lot of those in Iceland. And I could probably show you an Iceland fissure eruption because I have one here. This is pretty cool. So 1 second. So this is like a fissure eruption. This is Iceland though, okay? But very similar in terms of, Iceland and Hawaii are very similar. They're like, you know, brothers from another mother, something like that. Okay. When the activity became localized, a cinder and spatter cone given the Hawaiian name Pu'o was built. Over the next 3 years, the general eruptive pattern consisted of short periods, hours to days, when fountains of gas-rich lava sprayed skyward. Each event was followed by nearly a month of inactivity. By the summer of 1986, a new vent opened up 3 kilometers downrift. Here, smooth surface Pahoho lava formed a lava lake. Occasionally, the lake overflowed, but more often, the lava escaped through tunnels to feed Pahoho flows that moved down the southeastern flank of the volcano towards the sea. These flows destroyed nearly 100 rural homes, covering a major roadway, and eventually reached the ocean. Lava has been intermittently pouring into the ocean ever since, adding new land to the island of Hawaii. Situated just 32 kilometers or 20 miles off the southern coast of Kilauea, a submarine volcano, Lohi, it's been renamed since then, is also active. It has, however, another 930 meters or 3,100 feet to build up and grow before it breaks the surface of the Pacific Ocean. So we learned a lot about volcanoes today, differences between lava, magma, different types of magma, felsic, mafic, Kilauea, Mauna Loa, the Pahala Sill Complex, likely future directions of the Big Island of Hawaii going forward, because this is a very dynamic, ever-changing geologic landscape, and we have ample evidence over many, many hundreds of years, right, of thousands of years if you go through the geologic record, right, but even in our recent time frame of these devastating eruptions that can occur and destroy homes, cause loss of life, and more. So it's good to be very aware of what's happening, to track it, to follow it, and in my opinion, to be open-minded about this, because there are more connections than we realize as it relates to these volcanoes and the external environment, the Earth as a whole, and also the space environment, the sun, the cosmic environment, etc. For example, just interesting to note, we've been having this choppy solar activity for the past 7 days. We had Kilauea erupt shortly after we had the solar wind go negative, meaning it had a good connection to Earth's magnetic field. And we've seen this sort of activity and connection before. Now, I'm not saying the solar wind is 100% the trigger for an eruption at Kilauea, but you watch it enough and you notice that there's more of these little links and kind of like nods to each other than you would normally think if you were not following this closely. So our solar wind has been fairly normal, but we did start to get this nice connection right there. And then about just a couple hours afterwards is when we started having this eruption at Kilauea. And if we look at our recent solar activity, check this out. Here, we'll see this is past 7 days. You'll notice quite a bit of activity on the far side. So basically everything that you're seeing is activity on the far side, these big coronal mass ejections launching out. You'll see two or three pretty notable ones. So this is the 27th, now the 28th. This is when we started getting these weird sonic booms. If you've been tracking that, I've been doing live streams on that. But it's really the past couple of days that we've been seeing activity. So we'll see our first full halo come up soon. There's one right there. And we'll have another one come up soon. This is all, again, activity on the far side of the sun. And there's a nice ejection right there, and that's just the past 24 hours. So solar activity has been fairly low overall. Oh, there was one at the beginning. That's the one I meant to show you. It happened right at the beginning. So on the 26th, big far side eruption, another big one right there. Then we had two more that followed up just in the past few days. And just to quickly touch on our latest earthquakes before we get Kilauea back up and I sign off. We'll just go here. We'll switch this to the past week. Search by highest magnitude. And we see that our biggest earthquake activity for the past week has all been South America, finally changing the trend, because we've been having very little activity in South America for the past 18 months or so. In terms of high magnitude earthquakes, well, here we get a magnitude 6.9. This is on the 25th, 21:52 Universal Time, pretty deep, 109 kilometers down. Then we just, in the past 24 hours, have had a magnitude 6 that struck to the south. So here's the magnitude 6.9 right there. Here's the magnitude 6. Both of those not being magnitude 7s, but they are the strongest earthquakes during the past week. And we also see this double burst that struck the Western Indian Antarctic Ridge right here. Boom, boom. And if we go to our monthly view, zoom out, you'll notice that we had this 6.6 here, southeast Pacific rise. Then that was on the 20th. See that? Then on the 25th, we had the 6.9. Then you'll notice on the other side of that 6.6 is the double burst right here, right? That being on the 27th. So there was this seemingly kind of propagation of energy on both sides of the southeast Pacific rise. It's an area where the plates are spreading about 15 centimeters per year. Very fast plate spreading there, plate creation. Clearly a very important nexus point for plate tectonics as a whole. And so then we saw the 6.9, the 6.0, the 2 6s over here, and then you do also have this magnitude 6.7 that struck Japan just recently. And if we load in our activity, oh, here we go. I actually never created the video for the sun. We can do it right now. But we've been having these coronal holes on the sun that have been generating earthquakes. That's what it seems. The correlation is super, super clear. This 6.7 lined up with this coronal hole that we had last rotation. You see that's all the way back on the 15th. We're going to have that coronal hole return around the 13th or so in geoeffective position. So think about May 12th, May 13th, and about 2 weeks, we're going to be dealing with that. So I do expect there to be some higher magnitude earthquake activity around around 2 weeks from now. Kind of early, middle of June. I don't know why I'm, oh, okay, I know why. There we go. That should do it. So let me show you this coronal hole that we have right now. And here we do have a positive polarity trans-equatorial coronal hole. It's not that big, but it is fairly wide, and that will be geoeffective in just about 2 days. Maybe like, yeah, just about 2 days from now. So we could also get a bit of earthquake activity as a response to that in the next week, like from today to Friday. That's possible. Definitely something to watch versus there being really no factor elevating it over normal. So it is fairly wide. It's right on the equator. It's not that tall though. Earth isn't going to be surrounded in a huge area of low density, high velocity solar wind, but it will interact with that stream pretty distinctly for a solid day or two. Now, the one last thing I want to mention, because we were talking about all this gas within magma and the viscous and the activity and the explosive and all this stuff, right? Is we have this magma coming up at Hawaii, being from very deep in the mantle, from this hotspot, ultramafic, doesn't have usually that much of a volatile content, you know, these dissolved gases and water and such. Well, you have an interesting paradox here with Gakkel Ridge. So Gakkel Ridge is a supervolcano, and we're going to have to go up here to get to it. Here's Gakkel Ridge. This is the slowest spreading center in the world at only about 1 centimeter per year and even less than that in certain spots. For example, in the bottom of this massive caldera, a huge depression in the ocean floor that has a volume about 3,000 cubic kilometers. Huge. Suspected to be from a supervolcano eruption. You know, I can measure this. You're probably like, how big is it? Well, let's look at it. Yeah, it's 52 kilometers across, folks. That's huge. If you go this way, it's like 100 kilometers across. This is a huge, huge, huge depression. And again, let's measure this way. We'll get that cross-section view of it. You know, it's very significant. 3,500 meters, going down to 5,000, then going back up. So this is 1,500 meters deep, and it looks even deeper over here, right? This is like the shallow end of it. This is a huge depression in the oceanic crust, which isn't that thick to begin with. This is the Gakkel caldera, thought to be from a supervolcano eruption about 1.1 million years ago. Very slow spreading here. The hypothesis, with a lot of data supports, is that the reason the spreading is so slow here is because some of the energy from the convection of the mantle that expresses itself at the top of the planet, again, this is the North Pole here, right? The very top of the planet, see? It builds up in these magma reservoirs and then explosively releases. Now, what they've done is they've sampled the rocks at the bottom of the ocean here. And they've done seismic reflection surveys. And so they've shown with seismic reflection that the crust is very, very thin. And some geologists are even stating that you have parts here where the mantle is directly exposed to the ocean. Effectively at Gakkel caldera, you may even have the mantle directly exposed because you're getting these like pyroxene and peridot and other chemicals and minerals that you basically don't see unless it's from a deep mantle source. Additionally, they have observed that the carbon dioxide content of these magmas is huge, like 10 orders of magnitude more than normal. So they measure them at 13.5%. And again, we talked about earlier, typically, a mafic magma doesn't have that much of a volatile percentage. But here, it's ultramafic and it has a supercharged carbon dioxide percentage, which is one reason it was so explosive. Because sticky magma, while the silicious magma, oh my God, the silicious magma is high silicon based, it can explode like crazy, like Pinatubo, for example, right? Often it does cool in place, solidify, and that's all she wrote. But if you do have a magma that can move very rapidly because it's, very it's very high viscosity, it can move around very easily, right? It's like water, not honey. But it does have a high volatile percentage. If the pressure drops, all of a sudden, boom, shakalaka. That's what happened here. So interesting to see the differences between Gakkel Ridge and Gakkel Supervolcano and Hawaii, even though they both are fed from the deep, deep, deep mantle. Now, we have no evidence that we'll get a supervolcano eruption from Hawaii, because again, Gakkel Ridge has this order of magnitude higher CO2 percentage, but it's just showing the variation within the Earth. So really incredible stuff. I find it all quite exciting and wanted to share that with you today. You can look at some of our different views here before I sign off of the eruption. Let's make sure this is live. The fountains are definitely starting to die down, though they're still going. If I look at the tilt data right now, we're probably about 2/3 of the way done at this time. We've been live streaming for 6 hours and 30 minutes. And yeah, we're about 2/3 of the way done. So there's going to be about another 2-3 hours of lava fountain here at Kilauea before episode 48 comes to a close, which has been a record setter. Not because of the height of the lava fountains or the duration or anything like that, but because it is simply number 48. So Big things happening. As I discussed, I'll keep you up to date on all of it and much more. Thank you all so much for watching. I've been your host, Stefan Burns. Before I jump out, let's just quickly go through some of the questions that have come in via Superthanks. So thank you, Michael, for the super sticker. K-Harv, thank you as well. Reflections of a serial healer. Did you see the May 27th article in Science about pulsing magma plumes and their effect on rapid climate change? Explore some very interesting ideas. Yeah, I have that paper pulled up. I'll download it. I'll read it. So thanks for that tip, and I'll get on that, incorporate that into my research. So thank you. Capri, did you find the fireballs in Buffalo? You're probably talking about the sonic boom over New York and Boston and such. Yeah, we've been talking about that a lot on X. I have some live streams on that. I'll keep covering the fireball activity more. Thank you for your super thanks. What volcanoes erupts goes out of the atmosphere? Gases. Can they be connected with the sun? I'm not exactly sure what you're saying there. What's erupting out of a volcano? Well, we discussed that in depth with our presentation today. So I think your answer's probably been sufficiently answered. Your question's been answered. So thank you so much for the super thanks. Nirka Lopez, thank you for the super thanks. And a big super thanks from Caroline Brunquell. Thank you, Stefan, for being such a great teacher. We're lucky to have you. What are your thoughts on the environmental impact of the Blue Origin's explosion? Yeah, big explosion of the New Glenn rocket on the 28th of May in Florida. I think the biggest impact of that is just what gases were released into the atmosphere. That's not going to push the needle as it relates to climate change. But if we start getting, as these rocket eruptions and everything continue, and they go exponential in terms of how many rockets are being blasted off, it's not helping our atmosphere or our climate. Let's just say that. But one-off big explosion, I wouldn't want to be living near there and breathing that stuff in, right? Because the authorities are going to be like, oh, it's fine. And then 20 years later, they'll be handing out payouts for cancer. So personally, I'm not into it. They've shown with Vandenberg in California that all the crops, there's a lot of cropland around there, right? People are growing vegetables and stuff. They're all being contaminated by these weird rocket chemicals and such. So I personally wouldn't want to be breathing that in. That's an environmental impact, right? That's going into the ocean, sea creatures and more. So it's not good, but I don't think it's end of the world bad. Let's just say that. But we don't want more of those. So thank you for your very generous super thanks, and in general to everyone who has joined in on this live stream. Thank you so much for your interest, your time, your curiosity, your support, and more. Again, I've been your host, Stefan Burns. Smash that thumbs up button, help this channel grow, get this information out to more people. It's important that we learn more about our planet from a grounded but open-minded perspective. I do that. I release videos almost daily. We talk about earthquakes, volcanoes, space weather, solar activity, severe weather, geomagnetic storms. It's a lot. Planetary alignments and cosmic forces, consciousness, and everything. So if you like the sound of that, then we hope to see you around in more videos. And if you watch the channel but you're not subscribed and you're watching all the time, just click the button, folks. It doesn't do anything. And hey, later on down the line, you're like, you know what? I actually don't like this guy. Then desubscribe, right? I more so than having numbers, it's about having a group that resonates together, right? But if you're already watching the videos, and a lot of you are, but you're not subscribed, then click that button, because it does help push this content out to more curious individuals who simply just haven't seen it yet and learned because the algorithm just hasn't done so. So very grateful for all of you. I'm going to keep this live stream going for a bit, and then I'll close it down. But wishing you all well, and have a great one.
And the ground starts shaking. You know what time it is. Boomshakalaka, it's about to go down. Solar flare, fire lighting up the whole town. Boomshakalaka, the earth starts to quake. Predictions on point, watch the whole world shake. Magnetic fields are twisted, charged particles in the sky. Heat corners caught it on the live stream, now the flares are riding high. Seismic waves are rumbling, plates moving underground. Stefan drops the forecast, and boom, the proof is found. Boom, shakalaka, it's about to go down. Solar flare, fire lighting up the whole town. Boom, shakalaka, the earth starts to quake. Predictions on point, watch the whole world shake. Aurora start dancing, red, green, purple light. From space to the phone lines, he's calling it right. You feel that eruption, volcano starts to roar. Stefan hit the target like he's done it all before. From the sun to the stars, from the quake to the flood, every boom shakalaka hits harder